So these are some help videos for the Hardy-Weinberg equilibrium worksheet. I'm not going to do every single problem on this worksheet. I'm just going to do a couple overview problems. Again, you can watch this as many times as you need to. And then you should go ahead and practice some on your own. So we're going to start here with number 5. It says the allelic frequency for eye color in a population is 0.3 for the brown-eyed allele and 0.7 for the blue-eye allele. If brown eyes are dominant to blue eyes, what is the frequency for the genotypically recessive individuals? So one thing we're going to remember is that in Hardy-Weinberg, the P is for the dominant trait and the Q is for the recessive trait. So I'm going to kind of rewrite what I have here, and I'm going to see that P dominant is for brown eyes. So it says if the brown eyes are dominant. So my value for P is going to be 0.3, and that's for the brown eyes. And then I'm going to see that the recessive allele, blue eyes, Q, is 0.7. So I kind of just took what's from the problem, and I went ahead and I kind of wrote that in a different way. This question is not really asking you to calculate much. The question's saying, what is the frequency for the genotypically recessive individuals in the population? So one thing, the recessive individuals is going to be the Q. So you could just say for your answer that Q equals 0.7, which is the frequency. It kind of depends on what the problem's asking. You could also write it like this. 0.7 is equal to 70%. They're kind of the same number. I'm just rewriting it. It kind of depends on the question, how it's worded. If this was a multiple choice question, for example, you kind of look at, is the answer 0.7 or 70%? But that's really it. This one's quite simple. So now we're going to get a little bit more complicated with number 7. So it says the allele for unattached earlobes is dominant over the allele for attached. So I'm going to make a note and say unattached is dominant, which would be the P, and attached would be the recessive, which would be the Q. So little just notes for myself. It says in a population of 500 individuals, 25% show the recessive type. So 25% are recessive, and I just said that recessive is the Q, so 25% is the Q. How many individuals would you expect to be heterozygous for this trait? And I know, based on our PQ stuff, that heterozygous is going to look like PQ. So it's asking for how many. Notice it says how many, not the frequency. So I'm going to try to kind of write out what I have here. I know that 25% of 500 is going to give me the Q. So Q is 25%, okay? That is the frequency, the allele frequency, which remember can also be written like this. They're kind of interchangeable. So Q is, from the problem, is 0.25. Now, it's important with these problems that you always start with the recessive, the Q, because the only way to get a recessive trait showing is if you have double Q. So QQ is always going to equal the recessive trait. So I always start with my Q, and I can say that Q squared, which is the recessive trait, is equal to 0.25. So that's kind of always where you start. You always start with Q squared, essentially. And then from there, I'm just going to kind of work the problem. I'm going to remember we have two equations. One is Q plus P equals 1. And the second one is P squared plus 2PQ plus Q squared equals 1. So this one is for just the phenotype, and this one will be for the genotype. So to get Q, I'm going to take the square root of 0.25, because that's how you get Q by itself, and I'm going to get 0.5. So that gives me the value of Q. So Q is 0.5. From there, I can use this equation and say Q plus P equals 1. And I know that my Q is 0.5. And if I solve for P, I also get 0.5. So now I have two of the numbers I need for this equation. I'm looking for the heterozygous, the PQ, so I'm going to solve for that. Notice you can't use just Q plus P because there is no heterozygous in there. There is no trait. So I'm going to use that equation, P squared plus 2PQ plus Q squared equals 1. Now, for P squared, I can either calculate it ahead of time. I can do this. It's kind of just depending on what you want. Remember, 2PQ is the actual number you're looking for. You don't do anything with that 2. You just kind of use that as your variable. And then the same thing for Q squared. We know the value of Q squared and we know the value of Q. It really doesn't matter which one you use. You can just do 0.5 squared if you wanted. It kind of just depends on what you want to do mathematically. And then I'm going to work those numbers out. Remember 2PQ, the whole thing is what I'm solving for. So I just do 1 minus 0.25 to 0.25. So I get my value of the heterozygous to be 0.5 frequency. That is not the answer though, because it doesn't say what's the frequency. It says how many individuals. So you know that your original population is 500. So you're just going to say, okay, if you have 500 individuals, 0.5 of them are heterozygous, then the total number of individuals is going to be 250. So there is going to be a pattern with these problems. Number one, here's your two equations. This top one is for what it looks like only. The bottom one is for the alleles. If the problem says anything about heterozygous, which is P and Q, the only thing you can do is use this equation because it doesn't exist in the first one. You want to always find the Q, always find the frequency of the Q, the recessive trait, and then you're going to work the problem from there, finding the Q, finding the P, and usually solving for the PQ. All right, so we're going to do 9, and 9 is going to help us kind of figure out a little bit what these PQs mean. So it says in a certain population, the dominant phenotype, which again has the letter P, of a certain trait occurs 91% of the time. What is the frequency of the dominant allele? So this time it is asking for a frequency, which could be a percent or those decimal places. It's not asking for how many individuals. Now, you might initially say, okay, well, the frequency is 91%. The frequency of the dominant allele is 91%. Here's the problem. Just because the phenotype is dominant doesn't mean or doesn't tell you whether it's double dominant or one dominant and one recessive. So when we look at that 91%, right, which you can also write as 0.91, this is the dominant allele, which could be the P squared, which is what you would normally think, or it could be the 2PQ. So you can actually have the dominant allele as a double dominant or a piece of a heterozygous. There's no way to tell just from them saying that P equals 91%. So what you can do with this is figure out, again, we're going to start with the Q squared because that's kind of always where we want to go. Remember that P squared plus Q squared also equals 1. And you can say 1 minus 0.91 is going to be 0.09. Then we can solve for the Q like usual and get the Q to be 0.3. And then figure out P plus Q, which is P again, it's just the straight dominant allele, not the genotype. So we can say P plus 0.03. Sorry, that should be 0.03. Is going to equal 1. So P is equal to 0.7. You could say 70% there if you want. So again, the reason why this is not 91% is because some of those dominant phenotypes are heterozygous. They're not homozygous. They're not all 91% a dominant. Part of the 91% is heterozygous, which means there's a recessive allele in there. So to be able to tell how many are just straight dominant, you would have to do this math to figure out it's 0.7. So it's basically saying if 91% are showing the dominant trait, 0.7 or 70% have at least one dominant allele in them.